Okay, welcome to lecture number 5. We are actually going to do the synthesis of a cam for a radial roller follower. What I'm going to do is in the slides I have given you the construction process. I will go through this using GeoGebra step by step so that you get familiar with this. I'll do this both for the radial follower as well as for the offset follower. Okay, now the last tail end of the last lecture I was saying that we have seen the follower motion. I'm going to choose a 345 curve to basically go through the design. We assume that the cam is rotating anti-clockwise. The follower motion is as we have derived in the previous slides. The translating radial follower is what I'm going to choose. We start off the design by choosing the base circle radius, which is 35 mm in this case. This is an arbitrary choice. The size of the cam dictates is decided by this base circle radius. Now the roller radius again is also a parameter in the design. I have chosen that to be simply 5 mm small roller. The prime circle, which is basically the roller radius plus the base circle radius, is 40 mm. So now the question is, how do we proceed with these design choices? We are going to use the idea of kinematic inversion for the construction. We will see that I will show you an animation here. So you can see this is the idea behind this is that I assume that the cam is stationary, and then so if you are sitting on the cam, what you will see is that the follower basically is going to rotate clockwise because the cam is supposed to rotate anti-clockwise. And what you will notice is that the axis of translation basically rotates clockwise, but you also see the follower basically moving along that line. So that's basically what you will see. So when you sit on the cam, the follower has a combination of translation as well as rotation, which unlike from the fixed frame where it has a pure translation. Okay, so we will use this kind of an idea to basically come up with the cam design. All right. So before we proceed, I am going to assume the following things as far as the follower. I will also show you the final displacement diagram, and then I am picking off certain values. Now the rise period is 45 degrees of cam rotation. So from 0 to 45 I have the rise. Then we have a dwell for 22.5, which is 45 degrees to 67.5. Keep in mind that these are things that I have assumed based on typical values. These can change from problem to problem, and as I said, because we are doing engine valve, we are assuming we are having two dwells. It's not necessary that you should have two dwells. It's also not necessary that the rise and return periods rotations have to be the same. Okay, so 22.5 dwell is the first dwell, very short dwell, and then we have a return period again, which is 45 degrees of rotation. So what we are going to do is we are going to do this graphically. So therefore what I'm going to simply do is to pick off the follower displacement at 15-degree intervals in the rise and return period. So that means I have data at 0, obviously it's at 0 displacement, 15 degrees, 30 degrees, 45 degrees, of course it will reach the maximum lift. Then similarly in the return, the first point is going to be the maximum lift. Then I will look at 15 degrees after I start to return, 30 degrees after, which means 67.5 plus 15, which is 82.5, and then 97.5, and of course 112.5. It finally reaches the 0 displacement. So the visual representation of this is out here. So these are the points that I have. You can get this from the analytical setup, or you can get this from a graphical drawing of this curve. Either way is fine. I have done this analytically, so I have just picked out and I'm giving you values over here at 15 degrees and 97.5, because it is symmetric. Basically I have a displacement of 4.2 millimeters. The overall rise we have taken to be 20 millimeters. At 30 degrees, it is 15.8 millimeters, and so you can see it is not a linear thing. So 4.2, and then I am almost at 4 times the displacement, and then again a very short 4.2. displacement that it goes through to settle down at 20 mm. So 45 and 67.5 20 mm, 15.8 at 30 degrees and 82.5, and 15 degrees and 97.5 we will have 4.2 mm. So with this, so I now have the follower values marked out, so displacements marked out, and with this I'm going to start the construction. So let's go back, and I will now, I think I will switch to GeoGebra. So essentially to go through the construction process. Okay, let me hide this. So let's go through this step by step. I've already done the construction, so I'm going to kind of unhighlight or highlight as we go along, because to basically save time. Okay, so what I've done here is that we remember the prime circle that we have chosen is a 40 radius. So what I've done is to locate the center of this cam at this location A, which is minus 40 down the y-axis, so that when I look at the prime circle drawn, I will intersect the x-axis, or that x-axis is tangent to this. So this is the center of cam rotation A, and then I have this magenta is basically the prime circle. So now what do? We first divide this. So if you look at the circle, so now remember that we are going to sit on the cam, and then we are going to allow the so remember, actually the radial follower is going to translate back and forth out here. So now in the inversion, so which means we are going to assume that the cam is basically fixed. We are going to now draw effectively 15-degree lines first to represent the rise part. We picked off at 3 different points, right, at 15-degree intervals. So let me go search for that over here. I've already done this, so I'm just going to highlight those things as we go along. So the first segment is this I draw. Of course, the first line, basically this will be my AB, will be my, so this is my 0-degree line. So this is at 0 position, so let me draw that. And then we have at 15 degrees, I have drawn a line, so it has rotated clockwise by 15 degrees. Then we rotate further by another 15 degrees, 30 degrees. So this is the rise part of the curve that we are trying to design. Then we do one more 15 degrees, and we have reached the we have reached the end of the rise period, right? So so we draw at 15 degrees interval. So this is 15 degrees, 15 degrees, 15 degrees. So now we have reached the top, the maximum rise, which is 20 millimeters. Now then between the 45 degrees to 67.5, it is dwelling, so there is no motion, so we don't need to divide that into intervals. I can simply take the whole dwell period as one interval. So I will just draw a line. This is the line that I draw at 67.5. So this makes an angle of 67.5 from the vertical line. So remember, all these angles are marked from this. This is the actual axis of translation. What I've done is to rotate these clockwise. So first 15 degrees, 30 degrees, 45 degrees. Then this is the dwell portion, which is now marked at 67.5. We do the same for return. So let me go and do that for the return. I think this would be, no, this is the last one. Let me look at, I think Q, maybe that there's one more something sitting here. P. So that's the first segment. So this is 15 degrees from the first, from the dwell. This is the return, first 15 degrees. Then we have 30 degrees. And then finally I have my another 30 degrees, which I'm going to go through. So I draw another line. This is, so from here, this was the end of the dwell. Now 15, 15, 15. Now that comes to 0 displacement again. Now, of course, the from here all the way up to this is the second dwell. So it's a large dwell. So beyond this whole region, I don't have to divide anymore, because beyond 112.5 up to 360 degrees, I essentially up to back to this line is essentially the second dwell. So we leave it at that. Now what I'm going to do is effectively mark the displacements. The next thing that we want to do is to mark displacements along this vertical line. So that is what we are going to do. So let's draw those lines. Where are we? Yeah, so the first point, which is actually I should yeah, okay. So the first thing at 15 degrees, remember it was 4.2 3 something millimeters, 4.2 millimeters. The second point is at 15.72, which is at 30 degrees. And obviously the last point is going to be 20 millimeters, which is going to be so these are the 3 points. 15 degrees, the follower. So remember, this is the trace point of the roller follower. The trace point basically is the center of the roller. So initially at 0 degrees, it is going to be at 0 degrees, it is going to sit here. And then from N, it is going to basically move to O at 15 degrees of rise. 30 degrees, it will go to this point P, and then it will go to 20. Now, I have taken 15-degree increments. You can take whatever. You can take, for example, 9-degree increments. Then, the final cam profile that you get graphically will be a little smoother. So, just to illustrate the construction procedure, I have used 15 degrees. It's a little coarse, but that's simply to illustrate the procedure. Okay, I hope you have followed. So what we do is, along the vertical line, this is the lift at various positions. So when I start from N, which is the trace point, which is the center of the roller, is sitting at 0, which is the prime circle 0. Then I move from there by about 4.3 millimeters in 15 degrees rotation. I reach about 15.7 millimeters when I go to the next location, and then obviously I go to point Q, which is the final destination where I sit during the dwell. Then I return. So when I return, so the rise part is N to O, O to P, P to Q, and then I sit at Q for a while. Then I am going to return. So Q to P, P to O, and N, and then I remain at N all through. The trace point remains at that particular position. Now, what do we do? So what we are going to do is, remember that this position O, now the corresponding thing, this is at 15 degrees. So I have to now mark this along this 15-degree line. So what we basically do is to draw an arc. So we will draw an arc. Let me see what is the right arc that we have. Not the spline fits. Let me draw an arc here. Circular arc A, E, and O. So let me see. I think that's the right arc. Yeah. So you take a compass. You say I look at AO distance, and then I basically draw this arc, circular arc from O. So this now corresponds to the position of the trace point in the inversion. So I have rotated by 15 degrees. So this point O will now come and sit there. Okay. Now the next thing is to see the next arc, which is going to be AGP. So this is this point. So you do a similar thing at that. This represents 30 degrees rotation. So I draw a circular arc from P to the second line, which is at 30 degrees. Remember, this is the displacement at 30 degrees. And finally, I will do an arc from Q, and this will be basically sitting at 20 millimeters. Now, to locate at this, it has not moved between these two radial lines. It remains at the same position. So anyway, let us draw. It will be an extension of that arc. So if I draw that arc, I will get, what did I do? Okay, we will, where is I think, yeah, it has gone to, I probably missed, the sequence is kind of, yeah, okay. So, so you can see from there to there it dwells. So simply it's the same 20 millimeters. So 45 to 65 it is the same 20 millimeters. So therefore I simply extend the arc starting from here, draw the arc, and I will intersect this line 67.5 out here. So that gives me that. Then I'm going to complete the other. So this is another 15 degrees in return. It turns out to be, I think, this line, if I'm not mistaken. No. It is probably this line. Yeah. So I draw because it is symmetric at the same point P. So 15 degrees into return, I will be at point P again. So if I draw the arc, intersect 15 degrees from here, this is the intersection point. Now let us complete the other one. Sorry, I always click the wrong one. I think this is the one. So here we go. So again, now 30 degrees into the return, I at this position. So this is the location of the trace point. So what we are actually looking at is the intersections basically give the trace points. So I will turn on those trace points after I draw the various arcs. And the last one, of course, is going to be an arc which is going to be along the pitch circle, obviously. So corresponding to n when it comes and sits there. So this is going to be the final point. I'm just drawing that for the sake of drawing it. Okay, now let us mark all those intersections. We have M, which is the final trace point. L, which is this return point. K, which is where is K? K, which is basically so K, L, and M are in the return trace point locations in the return. I and J are basically those points, and then we have one more which is H, right? No, not H. Sorry. I, J, K, we need to have one more, right? Which is 15 and so I to J is basically 12. We need two more, which I think is G. Yeah, that is 1 point. And then what do we have? Let me see. I think point D. Yeah, E. Sorry, E. E is the first point in the rise, G is the second point in the rise, and I, of course, is the third point where you reach the top, and then from I to J, you remain at the same distance radially. And then J, K, L, M, finally you come back to the prime circle. Prime circle. So you will come and sit at that thing. So now we have got, N, E, G, I, J, K, L, M are basically the trace point locations at different cam rotation angles, right? So this kind of completes the construction of the cam, the pitch curve. So remember that the locus of the trace point is basically the pitch curve. So what we do next is, now that we have done all this, we are basically going to now say, okay, look, I need to kind of smoothly join N, E, G, I to J is of course a circular arc. So we basically do that. Here is the spline fits. So that will complete the construction of the prime circle. So I join, I do I am joining these, of course. When you do this in GeoGebra, you can use the spline command, but if you're doing it by hand, then essentially you are going to, kind of roughly draw that through the, so the return part of this looks like this. Where are we? What other? Have I missed out anything? I think, yeah, I and J is that black circle basically is going to, so if I want, I can kind of complete that arc, I guess. I think I may have A to H. Yeah, I don't think I have. That's fine. So, so you can see this is the pitch curve that I have got for the cam. So you see that here is the rise part of the pitch curve. The locus of the trace point is in this fashion. This is circular as expected because it is dwelling for a radial follower, and again this part is symmetric. You can see that these two look identical, and then I have a big circular part of the cam for the pitch curve, right? So this is the pitch curve construction that we go through. Let me quickly go back and then summarize this construction process. I hope you've understood this construction process. Let's go back and summarize this here. So here, what did we do? We drew this circle center over here. We marked the various positions out here. Of course, we can also draw. So first thing is we construct these 15-degree lines on the rise part. Similarly, for the dwell, of course, from rise to dwell, since it doesn't move, we don't partition that section. So we simply draw the dwell. Then in the return, we similarly drew 15-degree lines. And then from E prime 6 onwards, it remains basically the same till we reach the end of this, right? So having done that, then what we do is we draw circular arcs. This from B to G, first intersection, 15 degrees, then 30 degrees. In the inversion, it would have rotated to this position. So we move this point to this point located along the radial line. Similarly, at 45 degrees, D would be sitting at I in this inversion. And we do the same, of course, I to, from here it remains at the same radius. So we extend that, we get this for the dwell. Then for the return, we extend get K, L, and N as is shown here, right? and then of course it remains stationary for the rest of the part of the circle. So we do that, and now as I said, we'll join this, and then you get this pitch curve. So this is the pitch curve of the cam. Remember, we are doing a radial roller follower. Pitch curve is the locus of the trace point as it moves in the inversion, right? So this is what we have generated. Now, the next step is, of course, to basically draw the roller at each of these locations, right? 15 degrees, 30 degrees, 45 degrees, 67, 82, 97, and then, of course, 112.5. So remember that the center of the roller is basically on the pitch curve. So we draw now a set of circles, and the cam profile is basically something that is going to be tangent to these circles. Okay, so that is what you have to draw. Of course, if you take by hand, you can see that it is basically going to be something that you draw by joining drawing a curve which is tangent to all the roller circles. So these circles have been constructed with a radius RR, and then the centers are of course on the pitch curve. And what you draw is basically a profile. I've drawn that. Of course, I have used GeoGebra to make it look nice. You can do that by hand. Of course, it will be a crude way to do this, but very quickly we can see the shape of the cam. So now you can see that in order to deliver the kind of follower motion, this is the shape of the cam that I need to have. The green one is actually the cam that we have synthesized. Roller contacts the cam. The contact points are basically, you can see that Q, R, S, T, U, V, W. So if I look at Q, which is out here, R, S, T, U, V, W, and then I think this is P, if I'm not mistaken. So this are the contact points at those 15 degrees. Now you can make this curve a little better if you use more divisions. Of course, then the construction basically is a lot more involved as far as the process is concerned. Okay, I think now we have basically graphically done. Of course, note that from Q all the way to P, basically it is a circle which is offset. This distance is simply going to be 5 millimeters. So this is the base circle. So essentially 35 mm. This will be of 35 mm. So if I measure from A, the green line radius is basically 35 mm, which is your base circle. So effectively, we now designed a cam, and when this rotates anti-clockwise, and of course remember that the follower is actually going to be here in the real situation. Cam is going to rotate anti-clockwise, and then it will move back and forth. So I will um, stop here, and what we will do in the next lecture is to basically do the same process for a follower which is basically offset from the center, right? So instead of the translating line being radial passing through the center of cam rotation, I will choose it to be on this side. You can also choose it to be on the other side. Either way is possible. Okay, so this is how graphically you will construct the cam profile. So this is one of the cams that we have constructed for the intake valve that we have. All right, I will stop here.